All right, let's just jump right into this explainer. Today, we're looking at one of the greatest geological detective stories of all time, the incredibly dynamic, restless surface of our planet. For the longest time, we all sort of thought the ground beneath our feet was this permanent, fixed foundation, right? Well, the rocks tell a completely different, wildly active story about the Earth. Seriously, pull up a world map sometime. It's a massive physical puzzle that practically jumped out at early mapmakers as soon as the first accurate atlases were drawn. Just look at the uncanny geometric fit of continents separated by thousands of miles of deep ocean. I mean, the eastern coastline of South America and the western coastline of Africa look exactly as if they were just ripped apart from a single piece of paper. Was it really just a coincidence?
Spoiler alert, it wasn't. It wasn't just the shapes of the landmasses that matched up perfectly. Geologists started finding these layered rock formations that abruptly stopped right at the beach in Brazil and picked up perfectly over in West Africa. And the real smoking gun, they found identical fossils of a primitive freshwater reptile called Mesosaurus on both continents. So unless this little freshwater lizard somehow stropped on a tiny scuba tank to cross a huge saltwater ocean, those two landmasses absolutely had to have been connected.
Which brings us to part one, Wegener's radical idea.
Back in 1912, this German meteorologist and Arctic explorer named Alfred Wegener decided to step way outside his lane. Looking at all these crazy anomalies, he built an overwhelmingly logical case for a massive, single landmass he called the continent, which we now call Pangaea. He didn't stop at the puzzle piece coastlines or the Mesosaurus either. He pointed to mountain ranges, like the Appalachians in North America, perfectly aligning with mountains in northern Europe. He even highlighted paleoclimatic markers showing that tropical plant fossils were buried up in the freezing Arctic, while ancient glacier grooves were carved into rocks in places that are tropical today, like India. The only logical explanation? The continents themselves had actually moved. Now, you might think the scientific community would look at that incredible evidence and celebrate the guy. Yeah, no. The establishment of the early 20th century absolutely roasted Wegener. Geologists called his idea of continental displacement delirious ravings. They went so far as to diagnose him with made-up conditions like moving crust disease and wandering pole plague. The idea that solid rock continents could somehow just plow through solid ocean floors completely defied their illusion of a stationary, unmoving Earth. To be fair, Wegener's brilliant theory hit a massive roadblock. He lacked a plausible physical mechanism. How were they moving? He thought maybe centrifugal forces from Earth's rotation were pushing the continents, but physicists quickly proved those forces were way too weak to push through solid basalt. Without understanding the hidden mechanics deep underground, Wegener's theory was pretty much doomed to stay on the fringes of science for decades. Tragically, he died in 1930, way before he could see himself vindicated. But vindicated he was. Let's move on to Section 2, the engine of the Earth. It actually took submarines, sonar, and the massive technological push of World War II to finally peel back the oceans. When scientists began mapping the seafloor, they found something shocking. Massive underwater mountain ranges, like the Mid-Atlantic Ridge, running right down the middle of the oceans. Building on a 1945 idea about magmatic convection, American geologists Harry Hess and Robert Deitz realized in 1960 that the ocean floor wasn't static at all. By tracking magnetic pole reversals mirrored perfectly on either side of these ridges, they discovered a massive engine running deep underwater. They called this mechanism seafloor spreading. This was the missing link, the absolute eureka moment. The continents weren't plowing through the ocean floor like icebergs, like Wegener had guessed. Instead, the ocean floor itself is continually growing at these mid-ocean ridges, basically acting like a giant geological conveyor belt pushing the continental plates apart. Let's break down how this churning, dynamic conveyor belt actually works. Deep inside the Earth, intense heat makes the mantle incredibly hot and plastic. Convection currents drive this magma upward until it bursts through the surface crust at mid-ocean ridges. When that hot magma meets the freezing seawater, it solidifies into brand new rock. That spreading seafloor travels outward until it meets a lighter, thicker continental plate, where it gets shoved downward or subducted back into the mantle to melt and start the whole cycle over again. To really wrap your head around this, we have to visualize what we are actually standing on right now. You've got a solid inner core, a liquid outer core, and this massive, churning mantle. The crust, the solid ground where we build our cities and live our lives, is incredibly thin. It represents only about 1% of the planet's radius. We are essentially living on a shell as proportionately thin as a fragile eggshell floating on top of a churning sea of molten rock. All right, let's jump into section 3, the supercontinent cycle. Now that we know how this engine works, how does it shape the globe over deep time? Well, scientists have discovered that Earth operates on this immense rhythmic time frame known as the supercontinent cycle. Roughly every 400 to 600 million years, tectonic plates smash all the land masses together into giant single supercontinents. And then the internal heat forces them to tear apart again. It's a continuous, never-ending loop. When you look at the timeline, the sheer scale of ancient Earth is wild. Pangaea wasn't the first, not even close. Going back billions of years, we've had Columbia, Rodinia, and Gondwana. The ground beneath you has been endlessly assembled, smashed together, broken apart, and recycled over eons. But let's zoom in on Pangaea, our most recent supercontinent, which formed about 335 million years ago. It was this colossal C-shaped mass stretching almost pole to pole. And because all the land on Earth was clustered onto just one side of the globe, the rest of the planet was covered by a single, unimaginably huge superocean called Pangaea. As you can guess, this created a world of absolute extremes. Mashing all the continents together completely wrecked the global climate. Sure, the coastal areas were lush and tropical, but the deep interior of Pangaea was totally cut off from ocean moisture. It formed these hyper-arid, massive deserts blasted by high-intensity monsoonal winds. On top of that, this giant landmass blocked ocean currents, leading to severe stagnation in the water. That lack of oceanic oxygen was a massive factor in the devastating Permian-Triassic mass extinction, which wiped out 95% of all marine species. Brutal. But here's the crazy irony. The violent rifting and tearing apart of Pangaea, starting around 175 million years ago, was actually the catalyst for the world we know today. As the landmass split, water rushed in to form the Atlantic Ocean. That fragmentation shaped our 7 modern continents and isolated different species, which completely turbocharged evolutionary biodiversity, especially during the age of the dinosaurs. You might be wondering, how does a continent that big actually break? Modern seismic tech shows us that when a supercontinent forms, an external ring of subduction zones develops around its edges. Underneath, deep in the mantle, massive heat anomalies build up. We call them LLSVPs. They act almost like geodynamic blowtorches, forcefully pushing upward until they literally fracture the supercontinent from beneath, sending the continents drifting back outward toward those subduction zones. Which leads us to our final section, Earth's next supercontinent. Knowing that this cycle is continuous, we have to ask the obvious question: what happens next? Scientists use current tectonic plate trajectories to debate 2 main models for our deep future. You've got introversion, where continents reverse course and close back up over internal oceans like the Atlantic. And then there's orthoversion, where continents slide 90 degrees to assemble over the poles or the current Pacific Ring of Fire. This leaves us with 2 incredibly fascinating future scenarios for about 250 million years from now. In the Novo-Pangaea model, the Pacific Ocean completely closes up, slamming the Americas right back into Asia. In the Imagia model, the Americas, Eurasia, and Africa drift north, obliterate the Arctic Ocean, and spectacularly crash into each other right at the North Pole, leaving Antarctica completely stranded at the bottom of the world. But regardless of the exact layout, the next supercontinent, often called Pangaea Proxima, carries some terrifying stakes. Just like last time, mashing the continents together will likely create a hostile, unlivable interior. Climate models suggest we could see extreme interior deserts with temperatures hitting 55 degrees Celsius, that's 131 degrees Fahrenheit. An environment that harsh could easily drive most land mammals, potentially including any distant descendants of humans, straight to extinction. It's a pretty humbling reality check, isn't it? We build our monuments, draw our borders, and write our histories on what feels like solid, permanent ground. But when you zoom out and look at the epic, macro-scale geological forces constantly churning beneath the crust, you realize that the map of the world we know today is really just a temporary snapshot in an ongoing billion-year-old movie. Ultimately, Earth is still changing right now. The Atlantic is getting wider, the Pacific is shrinking, and the Himalayas are still being pushed up into the sky. We are simply passengers standing on a giant raft, adrift on a sea of molten rock. So, when Pangaea Proxima inevitably forms, will anything resembling humanity find a way to survive the crushing heat? Or will our civilization just become another layer of fossils hidden in the rocks? Thanks for joining me on This Explainer, and always keep questioning the ground beneath your feet.